All right, good morning, ShmooCon. So just a few announcements. T-shirts are available for donation. This year's T-shirts are available for a $15 donation. Again, we don't make any profit off of those. You're giving a donation to one of 3 charities, and we give you a T-shirt as reward. So we're not collecting any profit off of that. We're not making any money. All the money goes directly to charity. Last year's T-shirts, as well as a handful of bags from previous cons, will be available for $10. So if you're interested in shirts from previous conferences, that'll be available in about 2 hours at registration. As usual, we have a handful of things to hand out. I'm just going to toss these out. A pre-shuffled ShmooCon Rubik's Cube. So please wake up because this might hurt. Woo! And from Grimm, if you've not seen them out front, they have what would be the guts of a car that you can plug in and learn to use a CAN bus. So this is a medium. So not very many people in the audience can fit. Can you fit a medium? You can fit a medium. Well, not you, but the one in front of you. Yeah. So there's a reason that I don't play football. I hack things. All right. So without any further ado, I would like to introduce Mark and Matt. What I've been told about them is one speaks English, and the other just bought his 3rd pair of pants. So, for those of you that bought into the Kickstarter for HackRF and have no idea what to do with it, this is the talk for you. So, a primer on wireless reverse engineering. So, please give a warm ShmooCon welcome to Mark and Matt.
Hello, everyone. Thanks so much for coming so early on Saturday morning. I'm Matt Knight. This is Marc Newlin. We're researchers with Bastille. And for the next hour or so, we're going to be talking about some of the fundamental knowledge that you need to know in order to get into reverse engineering wireless systems. It's sort of a primer on wireless reverse engineering. It's going to be anchored by a methodology that we're going to propose that you're going to be able to use and apply to a variety of different wireless PHYs to start to reverse engineer them. I'm standing here with Marc Newlin. He's a cybersecurity researcher with Bastille. You may know him from discovering the Mousechuck vulnerability in 2016. One of the things that's interesting about Mark is that he got into wireless through a fairly non-traditional path. And that was by way of several of these DARPA challenges. So in 2010, DARPA had the Shredder Challenge, which was a challenge to reassemble shredded documents based on computer vision. And the entry was open for 3 weeks, and there were over 9,000 entrants. And Mark finished in 3rd, despite having no idea what computer vision was prior to paying attention to the challenge. He just thought it was cool and figured it out. He had such a good time with that first DARPA challenge that when DARPA came up with their Spectrum challenge in 2013, he said, well, I might as well give that a go. I don't know what this software-defined radio thing is, but how hard could it be? The first one was fun. So spoiler alert, Mark came in 2nd in that as well. And he did both of those things despite having never gone to college and not being an electrical engineer. So he's super smart, and that's Mark.
So Matt is a software engineer and researcher at Bastille. He works with me on the threat research team. Matt is very good at math because he did go to college. He's got a bachelor's in electrical engineering from Dartmouth College. Matt's been in the news lately for reverse engineering the physical layer of the LoRa low-power wide area network protocol. Matt is just a very talented researcher, just kind of a badass embedded systems guy.
Okay, so just a quick word on who this talk is for. So if you're in this room, obviously you've come to ShmooCon. Clearly you have an interest in information security. You've probably written some software before or done some scripting. You know your way around computers and you're good at getting them to work for you. You may not have any wireless knowledge, and that's just fine. We're not going to assume any prior knowledge in the wireless space. We're going to provide just the fundamentals you need to get started, but we're not going to overload you with math or any of the concepts that, frankly, we don't feel that you really need to get started in the space. And why should you care about this? Well, it's 2017 and wireless systems are everywhere. The Cisco Internet Business Solutions Group has a figure that we really like that states that by 2020, there are going to be 50 billion devices connected to the internet in some way. Obviously, that's being driven primarily by mobile and the Internet of Things. And as a result of both of those, fewer of these devices that are coming online are being connected with wires. So just a quick word on the Internet of Things. Apart from being the tech media's favorite buzzword du jour, what does it actually refer to? Again, if we're in this room, we're savvy enough to know that the Internet of Things is really just a bunch of connected embedded devices. And as we know, these quote-unquote smart devices are usually pretty dumb. We've seen it over and over again. And there's a good reason for that. And that's that these embedded systems are, by definition, built and architected around compromise. They often have extreme limits on the hardware they can use in terms of physical size and cost. They might be battery powered, which limits the extent and the type of computation you can do on them. They may be deployed in hard to reach locations, so often they'll need a special wireless link to talk to them, and they'll have to be easily configurable. It might not be super elite systems administrator hooking them up. It might be some guy who drives a truck, so they have to be interoperable. And oftentimes you can't get updates to them. They might have one-time programmable memory that you physically cannot rewrite, and there may be a network limitation. Perhaps there's too narrow a pipe to deploy a firmware update to. So you could argue that these embedded systems are vulnerable by virtue of being constrained. It's built into their architecture. It's part of what makes them capable to fill the role that they do, is the fact that they're built to a price point and a capability level that matches that job. But of course, there are implications down the road as to their security. And I'm going to point to two examples that will illustrate some of the types of wireless vulnerabilities that exist because of embedded systems architecture. The first is a series of vulnerabilities found by our colleague Logan Lamb in home alarm systems. In 2014, he studied the legacy RF link that connects the sensors that you deploy on your door and window, the RF link that connects those sensors back to the home alarm panel that manages all of the alarm state reporting. And he found that really with very little effort, he was able to jam those signals to deny all alarms getting reported to the police, and also do command injections so that he could trigger false alarms and do all sorts of other things to mess with his neighbors. He was also able to do some pretty spooky SIGINT-y things, like eavesdropping on people's alarm systems to figure out whether they were home, where they were in their house, et cetera, things like that. And the reason why he was able to compromise this link so easily is because it's this ancient one-way protocol that was designed to trade on security and capability, but got back extremely high endurance on battery and is very legacy tolerant. So he was able to compromise that pretty easily. Second example I'll point to is MouseJack, which was discovered by this guy right here. So in 2015, Mark studied the RF link that exists between non-Bluetooth wireless keyboards and mice and the dongles that you plug into your computer, which is hundreds of millions of devices. There are literally hundreds of millions of these keyboards and mice out there. And he was able to determine that he could execute some form of command injection or eavesdropping on just about every single one of them. And again, that was based on some embedded trade-offs that the developers of those devices were willing to accept, but that he was able to exploit. And I'm going to paraphrase Mark on something he said after this. When Mark observed that when he was getting into information security research, he was under the impression that it would be hard. However, in doing this, he was really shocked to find just how easy it is to find some of these devices and just how severe they can be.
So at the IoT Village at DEF CON last year, Matt and I gave a talk on reverse engineering a wireless drone, and we looked at this kind of hobby-level air hogs device. And the talk itself was centered around this one specific device, but we had a short section in the beginning where we talked about some RF fundamentals and some of the basic tools and techniques that we were going to be using. And the feedback we got was that people really enjoyed that section, and they thought before this that all this RF stuff was going to be hard and daunting and require a lot of education, when that's really not the case. So a lot of people think that you really need a PhD to do meaningful work in the wireless space, but that's absolutely not the case. And as Matt and I have demonstrated, myself with no college, Matt with just a bachelor's degree, you can really apply your existing software and reverse engineering skills to this space by leveraging tools that are already out there. So we're going to start by providing some background on the tools and software that you're going to want to know about and be able to use in this space. We're then going to do a pretty short crash course on some of the RF fundamentals and concepts we'll be talking about. And we're not going to get into any of the math or any of that, but just some high-level concepts that you'll want to understand. We're then going to introduce a RF reverse engineering workflow that can be applied to basically any wireless system. And the concept here is that you can go through these same steps looking at any device and come out with bits and bytes on your computer that you can operate on. We're then going to demonstrate this workflow across 3 different devices. We're going to look at a Z-Wave appliance module, then we'll look at a wireless doorbell, and finally a wireless keyboard. And the workflow is really what it's all about. You know, it's this process that you can go through and look at any different wireless device, leverage these existing tools, and get the information you want. And we're definitely not going to get into any DSP or math. This is outside the scope of this talk, and you really don't need to know it. The nice thing is that all this is abstracted away by the tools we're going to be using. So when you're wanting to get into wireless hacking, there are a lot of good hardware and software tools that you might be aware of. You know, the really nice thing, software-defined radios used to be really expensive in the thousands of dollars. Now there are a number of good options for really hobby budget level SDRs to do meaningful work. When you're looking at radios, you have this distinction between hardware and software-defined radio. So a hardware-defined radio is going to be, you know, the Bluetooth chip in your laptop, the cellular modem in your phone. It's going to be an integrated circuit that's designed to speak one protocol very, very well, but it's not going to be reconfigurable. There's still some good research tools that are HDR. So there's the Ubertooth, which allows you to do, you know, Bluetooth sniffing. There's Yardstick 1 to look at sub-gigahertz narrowband protocols. There are these Nordic NRF24 dongles for looking at other Nordic-based devices. There's the AppEmote, which is a board that allows you to interact with Zigbee devices. Then on the SDR side, the big difference here is an SDR is going to be reconfigurable. So whereas a hardware-defined radio is going to have, you know, potentially one center frequency or one set of center frequencies, one protocol, one physical layer, with SDR, you can retune the radio to any arbitrary frequency, to any arbitrary bandwidth, and then the SDR streams this raw radio data to your host computer, and then software on the host computer does all the magic that interacts with different physical layers and protocols. So on the SDR side, we have the EDIS USRPs. These are really popular, starting around $700 and going to as much money as you're willing to give EDIS. There's the HackRF, which is a really good option, a really good, reasonably priced option at $300. And there's a BladeRF by Nuand. It's another really good option that's popular amongst hobbyists. And then there's some good software to go with these hardware tools. So on the SDR side, GNU Radio is, you know, really the most important tool that you want to learn. It is essentially a connection of different signal processing blocks and input and output blocks that you can tie together. So you might have a block to receive data from your radio and then do some demodulation and so forth. And all of this abstracts away all of the math that you don't actually have to know. At Bastille, we've contributed to the GNU Radio project through a couple out-of-tree modules. Matt produced GR LoRa, which is a GNU Radio module for interacting with the LoRa low-power wide area network protocol. I've released GR Nordic, which is a GNU Radio module for interacting with these Nordic Semiconductor NRF24L devices. And then BAUDLINE and Spectrum and Phosphor are a few tools for visualizing the radio spectrum on your computer. On the HDR side, there's the BlueStack, the Bluetooth stack that runs on Linux. There's libubertooth, which does the host processing for the Ubertooth. Killer B, which is a Zigbee stack that interacts with the AppEmote. And then I've released a Nordic NRF24 library for doing packet transmission and reception with these common dongles. And the thing I really want to drive home here is that the tool set in this space is just phenomenal. So you can be somebody like me with, you know, no formal education, no signal processing background, and you can come in and use these tools and do really interesting stuff.
Okay, so at this point we're going to start to get a little technical, and we're going to cover just the basic RF information that we feel you need to know in order to start working through some of these reverse engineering tasks. And I originally entitled this my obscenely short radio crash course, but really, after further thought, I think this is probably more appropriate. We're going to go through this at such a high level, and we're really going to strategically target what we cover. There's a lot more to go into, but we're going to focus on the really important concepts that we think are critical. Okay, so we're going to be talking about the physical layer. So if we have our well-loved OSI model, we're talking about layer 1 here. And if you're dealing with wireless protocols, that refers to, in wired protocols, it refers to the voltage and timing information of how your data bits get mapped into physical phenomena, physical properties, electrical properties. However, with wireless, rather than voltage and timing on a wire, instead we're talking about patterns of energy that get sent over an RF medium. RF stands for radio frequency. It's the electromagnetic energy that is just around us all the time. And as Tom Rondeau, one of the former GNU Radio project lead and now a DARPA program manager, likes to thump his chest and loudly proclaim, RF is one of the 4 fundamental forces of the universe, and with radio we can understand it. We can visualize it by using this tool called a spectrogram, or a waterfall. And we're going to be looking at a few of these over time, but the key thing, or throughout the course of the presentation, the key things to remember is that here we have time in the y-axis and frequency in the x-axis. And then the power is represented as the z-axis, or the intensity of the picture. So we can use this to visualize the spectrum, but what if we want to interact with it? Well, we can do so, we can manipulate the spectrum by using a device called a radio. And radios can be hardware defined, as Mark mentioned, where the radio and protocol-specific features are baked into silicon, such as that dev board on top, or the module on that dev board on top, or they can be software defined, where you have some flexible hardware that's capable of doing raw capture, and you let all of the protocol and radio-specific heavy lifting be done by a processor, or by software on a processor. And that can either be a CPU or an FPGA. And there's a USRP on the bottom. So when we talk about how these PHYs are built, one of the most important components to kind of get comfortable with is this notion of a modulation. And the modulation is simply a function that defines how the digital values in your layer 2 frame get mapped to RF energy. And there are 3 different electrical properties, physical properties that we can modulate here. We can modulate amplitude, power, frequency, the rate at which a periodic signal is changing, and phase, which is the phase offset into that periodic signal. And of course, we can put all 3 of those together and do some combinations to come up with more complicated modulations. But those are the 3 key properties that we're going to be talking about. Now, modulators can modulate analog or digital information, but we're going to be talking primarily about digital modulation modes. And in this context, there's this notion of a symbol. And this is one of the most important concepts to hold on to from this. A symbol simply represents a discretely sampled RF energy state that represents some quantity of information. So your modulator is basically going to take bits from your layer 2 frame, and in the process of doing its function, is going to produce these RF energy states that can then be sent to a radio, a software-defined radio, and sent over the air. So when you see some symbol, just remember RF energy state that has some meaning. We're going to illustrate this later. So there are several common IoT PHYs. We're just going to talk about 2 of them to kind of put some context in some of the concepts we've just discussed. And here are illustrations of 2 of them. On top, we have frequency shift keying, where the RF energy alternates between 2 frequencies to signify the underlying digital value that was modulated. And then on the bottom, we have amplitude shift keying, where instead of it being frequency, we're instead modulating the RF power on a static frequency. And that's how we represent the digital values. So symbols in this case can be illustrated as such. On top, with the frequency shift keying, we say that a symbol is the signal dwelling on one of those 2 frequencies for some discretely sampled amount of time. And you can visualize that, right? If the signal's on the left, you can say that it's a 0 at that instant. If it's on the right, you can say it's a 1. And it kind of makes some intuitive sense. And then on the bottom, we can say the same, make a similar inference about power, where if the signal is on and present, we can say, okay, that's a 1, and if it's off, it's a 0. So we can start to make some visual references as to what this is actually doing in the spectrum. Of course, there are more complicated PHYs. Really, the sky is the limit as to how much you can throw, how complicated they can get. But one thing you'll see from time to time is spread spectrum, where the data bits get encoded at a higher rate, and it causes them to occupy more spectrum, but it makes it more resilient to RF noise. And 2 examples of this are 802.15.4, which is the PHY MAC that Zigbee uses. There's a picture of that on the top there. And then the LoRaPHY is another example of a spread spectrum modulation that I've spent a bunch of time with. And there's a picture of that below. And that uses some other RF features as well to get some very high low power performance, a very good low power performance. So radios can have 2 functions. They can transmit and receive. If it can do both, it's dubbed a transceiver. But when we talk about reverse engineering systems, really our main objective here is to back out what a transmitter is doing by figuring out how it has mapped data into these RF symbols. So really, when we talk about reverse engineering wireless systems, it really boils down to building receivers. And it's not about transmitting, it's really about how well you can listen to these signals. So that's what we're going to be talking about. And it has 2 benefits here. We're going to learn how to reverse engineer systems, but also when you go home and have to explain to your spouse why you had to go to the security conference for a weekend, you can tell her in earnest it was so that you could learn how to be a better listener. Thank you. I'm here all weekend. Okay, so this brings us to the meat of our talk, which is this wireless reverse engineering methodology that we're going to propose. And we're going to begin with a little interactive session. So I'm just going to throw this picture out to the audience. I know it's a little grainy, but we'll do our best, and ask you to make some observations on it. Again, remember, this is a spectrogram. So we have time in the y-axis, and frequency in the x-axis, and then power in the z-axis. Anybody want to just make a comment on what they're seeing here? Yeah, exactly. Perfect. Yeah, so the modulation looks like a frequency shift keying. We just saw a picture of it. How many frequencies are strongly represented here? We just saw it. Yeah, there are 2 frequencies. So we can see the signal is alternating between 2 of them. And how about any timing information? Can we see anything in this picture that would give an indication as to the structure of the information here?
It looks like you got a header or idle signal and then data.
That's absolutely perfect. So it looks like the top half of the signal, it alternates consistently. It repeats the same pattern over and over again, which looks like a header of some sort. And then beneath it, the data starts moving a little bit faster, but it's also no longer abiding by that same static pattern. There are more changes in it. So we can start to infer that we have a header followed by some amount of data. And we'll robustify this as we go on, but I think it's important just to do that exercise so that we can start to look and gain some intuitive sense as to what's actually happening in the medium. Because you might look at a signal and it might look like a squiggly line in a spectrogram, but really there's meaning behind everything here. So don't be intimidated by it. You can look at these things and start to make assumptions about what they're actually doing. So let's formalize this process, right? We kind of just did this by talking through it. But step 1 is to characterize the channel. And that's to identify where on the spectrum does the signal exist. So that's looking for the center frequency, measuring how wide it is. If there's a frequency component in the modulation, the width of the channel, and then determining whether it's a single channel or if there are multiple channels the signal might hop between. Step 2 is to identify the modulation, which is by far the hardest and most intimidating part of all of this. Until you realize that most of these IoT and low complexity devices just use variations on the same few PHYs. So eventually you will gain some intuition as to what you're actually seeing when you look at these pictures. But until that happens, we're going to be able to lean very heavily on open source information and documentation to do that work for us. And we'll illustrate this momentarily. Step 3 is to determine the symbol rate of the transmission that we're observing. And there are a variety of tools that we can use. One that's super awesome is this tool called Spectrum, where you can basically drop cursors on a demodulated waveform and use it to measure out the timing of the symbol state changes. But we can also lean very heavily, again, on open source information and documentation to do all the heavy lifting for us. Step 4 is to synchronize a receiver against an incoming signal. And here we're gonna leverage that header information that the gentleman in the front row just commented on. We're going to identify the preamble and the start of frame delimiter synchronization fields that essentially every digital communication scheme has in some way. We're going to illustrate this as we go through some examples. And finally, we're going to extract the symbols. We're going to demap the symbols into the data that was modulated, into the data that they represent, and we're going to get back the bits out of the air. Cool. So we're going to show this in action now, but before we do that, my colleague Mark is going to say a few words about the power of open source intelligence.
So I'm very passionate about open source intelligence, and the reason is that OSINT allows us to really be lazy. If you can go and find information that somebody else has already discovered or has been documented somewhere, that cuts down on the time that you have to do this hard work. So a good source of this data is going to be FCC documentation. So if you're a company and you want to sell a wireless transmitter that's not test equipment in the United States, you have to send this device to a test lab, and the test lab evaluates the properties of the RF emissions. So the test lab has to verify, what frequency does this device operate at, what power does it transmit at, what is its duty cycle. In some cases, the test labs will include modulation information or packet formats, and then all this data is sent to the FCC and is publicly searchable. So you can get a device, look at the FCCID, go online, and very quickly learn a lot about the physical layer characteristics of the device. Oftentimes, this is enough to fully implement a transceiver or receiver. Also on the FCC documentation, you have internal photos of devices. So you can look inside a device, see if there are any well-marked RF integrated circuits on there, and oftentimes you can find data sheets for these chips which will list known packet formats and protocols. Looking at patents for proprietary protocols is also very useful. If you're looking for more information on this OSINT process, I gave a talk at Hack in the Box last year on applying the FCC and regulatory data to the reverse engineering process.
Cool. So we can update our methodology to include open source intelligence gathering really as a step 0. Before we do any radio stuff, we're going to do as much research as we can and figure out what's already been done for us so we don't have to reinvent the wheel. Because radio is hard and we're lazy, so we want to make this easy. All right, let's get into some examples. So the first PHY we're going to have a look at is a frequency shift keying PHY that is used by the Z-Wave home automation protocol. And again, I just want to reiterate, we don't really care what the device is in this case. We're only using this because we want to show off one type of PHY. This could be anything. It doesn't really matter that it's a home control protocol. We're just using this so that we can get bits out of it. What the application's doing is we're really agnostic to it. So home automation protocol, it's full stack, and it's also closed source. So everything from the PHY up to the application is proprietary and is not publicly available. So let's build a PHY to enable some hypothetical analysis of upper layers. Okay, start with step 0 with some open source intelligence gathering. We have our device here, which is a Z-Wave appliance module. We can look at the bottom of it, and we get all this silkscreened information on the enclosure. Well, the FCC ID is printed right there, and that's because the FCC requires that this ID be printed on, is it every transmitter? Or there are some requirements, but pretty much any IoT or home device that you're going to be looking at is going to have this printed right there in clear text. So we pull this out, we plug it into one of the many available FCC ID search engines online, and there's our device. Those are the test photos that we pull out of the FCC report that we get back. You won't be able to see it in the projector, but you can actually read the FCC ID on that picture and validate that it's the same. Cool. And then if we pull up the test report and navigate through it, it's a long, boring document, but if we get down to section 3.1, the equipment under test section, we are given its operating frequency and its modulation, and it's right there in the document. Okay, that's pretty useful, but let's see what else we can find. Trolling through the rest of this document didn't reveal much, but since we know that it's a Z-Wave device, why don't we look at some other Z-Wave devices, look at their test reports, and see if there's any juicy information in that perhaps we can start to reference back to this device that we're looking at. So I did a generic search for Sigma Designs on the FCC website. Sigma Designs is the company that has made and maintains the Z-Wave stack. And we come up with a bunch of devices that could fit the bill. So just pick an arbitrary one, and here we go. We've got some great information. It's this, looks like a Z-Wave USB sniffing test tool of some sort. Again, we don't really care. We can read through the documentation here, and it tells us that, in fact, there are 3 different channels. Each channel has a different data rate. So we can start to make some inferences about the overall structure of the PHY. Now we're going to ignore channels 2 and 3 just for the sake of time, and we're going to focus on channel 1. So we're going to build a receiver for the 9600 bit per second variation of this PHY. Okay, so let's have a look at what we've gathered through our open source intelligence, right? We have channel information with the frequency and deviation, which is the width of the channel. We have information on the modulation, again, that was printed right there in the document. And then we have some information about the symbol rate. So just by doing some basic open source research, steps 1 through 3 of that 5-step process are done for us. So before we go any further, we'll validate, of course. We'll pull up our tools and we'll have a look. In the interest of timing, we're going to skip to the thing that stood out. There was one exception. One of these numbers wasn't quite accurate. And if you pull it up in the Spectrum and do the FSK DMOD, it's a built-in tool, it's really nice to use, and you measure out the symbol rate, you see that the symbol rate that we actually observe is 2x what it says in the document. Anybody here want to venture a guess as to why the symbol rate might be 2x what the bit rate is? What was that? No, that's a good guess, but anybody else? I heard it. Manchester encoding. Bingo. So Manchester encoding is a type of it's a type of encoding that's applied to a variety of wired and wireless communication systems. Don't really have to know what it does, but what ultimately the core concept behind it is it encodes the data such that no more than 2 adjacent symbols can have the same value. And what that does is it induces lots of state changes and randomness in your data. And the advantage for radios is that it's really good to have random information for receivers because they can use it to synchronize against. And you can think about, in the context of FSK, what would happen if you didn't encode a datagram that was just all zeros. right? If you think about the modulation, the spectrogram that we looked at, you would just have a straight line going down on one of those two frequencies. And when you're trying to recover timing information, that's obviously not super helpful. So by having all these state changes, we give lots of little edges for the radio to look at. Again, it's a bit of a detail. We're not going to worry about it too much. The key thing that we need to know is that we need to update that bit rate to reflect the actual symbol rate. So the symbol rate's actually going to be 2x what the bit rate in the document said. Okay, so we go back to our methodology, and we're already 2/3 of the way done, just by doing a little bit of research. So at this point, what we can do is we can translate that information that we pulled out of the open source research into a GNU radio flow graph. And the GNU radio flow graph is going to do all of the hard RF stuff for us. And I'll show you a picture of what it looks like in a minute, but it's a really generic design. We're going to release it online. You'll be able to take it and apply it to other FSK signals that you might encounter. And you'll just be able to change the variable values, and you'll be off to the races. But the GNU radio flow graph is going to do the radio part and hand us a stream of bits, just a stream of ones and zeros. And at that point, we have bits on a disk. And if you're here at ShmooCon, you've probably dealt with a binary network protocol before, or binary data in some format. You're going to be able to apply your normal computer science and information security skills to that to work through it. So once you get past steps 1 through 3, which you can solve with open source information, you can apply the skills that you already have to this to work through these protocols really quickly. So here's the flow graph. There are 3 elements I want to call out. Ultimately, that first block that we've circled is doing step 1, channelization. The second part here is doing demodulation. I know there's that scary looking floating point constant in there, but I assure you, all I did was create some variables that filled in the auto-populated equation in that. So if you open up that block, it already has the equation. It takes in, I think, it's 2 times pi times like the deviation divided by the width of the channel divided by the sample rate or something like that. It's already populated in there. All you have to do is populate those constants, and that value gets filled out. And we know what the constants are because we got it out of the docs. And then step 3, clock recovery, looks really scary. 4 of those 5 variables in there are the GNU radio constants, and the only one that has been updated is the first one, omega, which is mapped to a variable that you can just replace. And that is going to correlate the rate of the input data to the symbol rate that we're expecting. And we're going to release this so you'll be able to take this and apply it to other FSK signals you see. So at this point, we have bits. We've gotten bits. We've solved the radio part, and we have bits in our computer that we can work with any tool that we want. So here's some pseudocode. I have it implemented in Python that I'll show you in just a minute. But ultimately, we're going to do the process that we talked through earlier. We're going to look for the preamble and start a frame delimiter, that header information in the signal that we're seeing, to identify that we're about to receive a packet. Then once we're synchronized, we're going to read out the bits, de-Manchester encode them, and then parse them out. So it's time for a quick little demo. Again, all these tools are going to be released, so you'll be able to look through them in greater detail. But basically, I'm firing up my GNU radio flow graph here in GRC. Same thing I just showed you. And then over in this shell, I'm going to run my Python decoder. And I've got the device plugged in down here. I'll create some traffic, and you'll see some frames. So there we go. Again, we don't really care what the information in the application layer is. We really just want to show that we can get information out of this RF out of this wireless PHY just by doing a little bit of open source information and being able to fill in the gaps. All right, so with that, I'm going to hand it off to Mark.
So now we'll take a look at another low complexity physical layer. In this case, it's with this wireless doorbell. And we're looking at the Heath Zenith SL7762. And the way this works, you have a receiver, which is this box here, which has some batteries and a radio receiver and a speaker in it. And then you have a transmitter, which is this doorbell button. And so you press the button, it sends a packet to the doorbell, and then it plays this chime. The doorbell button itself, or the doorbell itself, comes with 2 buttons. So you have 2 buttons that can play 2 different chimes. Because the chime is receive only, it doesn't actually transmit, it doesn't need to go through the same FCC certification process. So in this case, we only have a FCCID for the doorbell button, but we can start our open source intelligence there. So we pull up the FCC exhibits for this doorbell button, and we have a lot of irrelevant stuff, but we also have this test report, which contains these RF characteristics as identified by the test lab. So we pull up the test report and we look in the product description section here, and we can see right away that this is a 315 megahertz center frequency. So already we know some of the channel information about this device. Further down in the test report, we have this discussion of pulse desensitization. And we see here that we have a 320 microsecond duration bit 1. And this tells us some interesting information, which is that this is likely going to be a pulse width modulation. And this is a type of on-off keying or amplitude shift keying where we're encoding data based on how long the transmitter remains on. So this is telling us that to communicate a bit 1, the doorbell button is going to turn its radio on for 320 microseconds and then turn off. Down here, we can infer that we have a 13-bit packet length. We have this equation which says 0.32 times 5 plus 0.72 times 8. So we can see that we have 5 1 bits in the packet that the test lab looked at, and then we can infer that the 0.72 refers to the duration of the bit 0, and then we would have 8 0 bits in this example packet. So now we know the duration of the bit 1, duration of the bit 0, as well as the total number of bits in the packet. Down here we see that it's a 25 millisecond duration or packet spacing, and this is telling us something interesting, which is that either we have a large spacing between each 1 and 0, or that we have a packet that's transmitted followed by some predefined gap. And so that gives us a 30% duty cycle, meaning when you are actively operating the doorbell button, it is only transmitting from the radio 30% of the time. So this is an image from further on in the test report, and this is a time domain visualization of a single packet. So on the x-axis we have time, and on the y-axis we have power. And this lines up with the information we saw from earlier in the test report, where we had these 13 vertical bars, each representing 1 bit. So the leftmost bar is a skinny bar. This is going to be a 300 microsecond bit 1, followed by a 700 microsecond bit 0. And we can see from the legend on the bottom there that each bit is approximately 1 millisecond in duration. So that tells us that for a bit 1, we're going to have the radio off for 700 microseconds and on for 300. And for a bit 0, we're going to have the radio off for 300 microseconds and on for 700. And the problem is we don't actually know yet what these bits mean. And there wasn't any further data in the test report from this particular doorbell, but looking through the FCC documentation, I found an older doorbell from the same manufacturer, and it has some good information here. And this says the data rate is approximately 1 kilohertz, and the pattern consists of 8 address bits, 4 data bits, and 1 start bit, which gives us 13 bits total. And this lines up with what we've seen, so we can assume that this packet format will apply to our doorbell as well. So that means we're going to have this 1 kilohertz data rate, we'll have an 8-bit address, which we can assume is the unique identifier of the doorbell button, and then we'll have a 4-bit data section. And because the doorbell button can transmit different tones, we can assume that that 4 bits is going to represent an identifier for the specific tone. So now we can do a SANITY check, and we can actually pull up BAUDLINE, the spectrum visualization tool using GNU Radio. So this is kind of a bare minimum simple flow graph. We have our USRP source, which is our software-defined radio, and that is simply sending data into BAUDLINE. And we can see in this image here on the right, this is the visualization of the doorbell button. So we have 13 bits here. We have the skinny 1 bits and the wide long bits, or wide 0 bits. So this tells us that the OSINT information we have matches up with what we're seeing over the air. And in this case, I ended up getting a couple of these doorbell sets, looked at the 4 different doorbell buttons, and everything lines up. So we have the start of frame bit, we have the button ID, and then we have the tone ID. And so from OSINT alone in this case, we've learned enough information to actually implement a transceiver and a receiver. So we've learned the channel, which is a 315 megahertz center frequency. We've learned that it's pulse width modulation. We've got the symbol timing, which is this 1 kilohertz data rate. We know what a bit 0 looks like and a bit 1. We've been able to synchronize a packet by determining the packet format, which is the start bit, the button ID, and the tone ID. So we can take this information and then actually implement some simple GNU Radio Python code to interact with this doorbell. And depending on your level of comfort, some people like using GNU Radio Companion and doing flow graphs. I prefer to work in code. So this is just a Python example. You have the class here called a top block. This is just some GNU Radio nomenclature. We have our USRP source here. This is just a software-defined radio instance. We run that through a low-pass filter. We then have these next 2 blocks here which tell us the output power. And so what we're doing is we are telling the software-defined radio to record this data, and then we're computing the decibel power of this doorbell button because we care about, is a transmitter turned on or off. Then we have this threshold block which will output either a bunch of 1s or a bunch of 0s depending on whether or not the doorbell button is above or below a certain threshold. So this gives us a bit stream that tells us whether or not the doorbell is transmitting or is turned off. We can then send those bits into this doorbell framer class, and this is just some simple logic to look for that packet format. And so again, because we have a bit 1 represented by 700 microseconds of the radio transmitter being off and 300 microseconds being on, we know that we're going to have a period of low level, followed by a period of a high level, and then followed by a period of low level. And so when we see that low to high to low transition, we know we've seen a bit. So after we see that transition, we look to see how long the transmitter was high. We say if it is 400 microseconds or less, we call it a bit 1, otherwise we call it a bit 0. And then when we've received 13 bits, we know we have a packet, and so we can pack 8 of those bits into the button ID and 4 of those bits into the tone ID, and then we can print this out to standard out. So I'll go and run this script here and we'll decode the packet from this doorbell. Okay, so we can see that we have button ID 249 and tone ID 1. Now in this case, because it's a very simple protocol, we can do the inverse pretty easily. So I have a transmitter script here, and we start with a tone, just a simple cosine wave, and without modifying this, we just send this wave to the radio, and then it's always going to be transmitting. So we need to modulate this somehow and turn it on or off. And the easiest way to do that is just multiply this generated signal with some 1s or 0s. So we have a mask here for bit 0, which is just 300 microseconds worth of 0s and 700 microseconds worth of 1s. And then for bit 1, we have 700 microseconds worth of 0s and 300 microseconds worth of 1s. And then to generate our packet mask, we take an input button ID and just concatenate a bunch of these bit 0 and bit 1 masks together to make this packet mask. And then we can multiply this mask by this automatically generated cosine wave and mimic the transmission of this doorbell button. So we'll go here and pass this into the doorbell transmitter script. So we have button ID 249 and tone 1 that we received from this. And now we've transmitted that using the SDR and shown that we can actually inject packets into the doorbell. And so I've noticed in the hotel, some of the rooms have these doorbells on the door. If you are in one of these rooms, come find me. I really want to be your friend. And so now let's look at another common device, in this case, a wireless keyboard. And we're going to be looking at the HP Classic Wireless Desktop Keyboard. And this is a keyboard and mouse set, but we're only going to be looking at the keyboard and dongle. So this is actually manufactured by an OEM called Acrox. It's an HP product. And because we have 3 distinct devices here, we have 3 distinct FCCIDs. And so we can start by looking at the FCC test report for the dongle. And we can see that it's GFSK modulation, 1 megabit per second data rate, and 78 channels. So we have a pretty good start here. Now we have the keyboard test report. Now this gives us some different information, which is kind of problematic. So we can still see the FSK modulation, which lines up, but this says a 2 megahertz channel bandwidth and 34 channels. So this is kind of confusing. And the channel bandwidth of 2 megahertz is not necessarily incompatible with a 1 megabit data rate. So we're going to assume that the data rate indicated by the dongle is correct. And then because this is a device we can plug into a computer, we can also get some information by plugging the dongle in and looking at the DMESG output. Here we see that it says the manufacturer is Mozart Semiconductor. So this is a case where we have a product with a brand on it that's made by some OEM with electronics by some other company. And so the OSINT has failed us a little bit and we need to break out the radio. So we can start by plugging the dongle in and looking across the spectrum using New Radio and BAUDLINE. And we see something interesting, which is that the dongle is camping on a single channel for the entire time. It's not doing any kind of hopping. It's only using one channel. So regardless of the different channel number counts in the different test reports, we can throw that out because we know it's operating on one channel. And we can also see that it's probably some kind of time division multiple access. The dongle is transmitting these packets every 8 milliseconds, and so we can infer that the keyboard and mouse will probably time synchronize to that and then transmit in other slots on that channel. So now we can do some typing on the keyboard, and this validates what we've inferred. And so we see that the dongle is transmitting these packets every 8 milliseconds. When we're typing actively, the keyboard then transmits its packets 2 milliseconds after each dongle packet. And so now we can actually use the information we've gathered to start to decode some data. So we'll start with the SDR source, go into our low-pass filter, do the demodulation, pack these bits into bytes, and then write it to disk. And what's going to happen, we'll press play, and then this GNU Radio flow graph will demodulate the channel that the keyboard and dongle exist in and save that to disk. Then we can operate it on disk like we would any other binary format. And I really like to use existing command line tools for doing this kind of thing. So we know that a lot of wireless protocols will start with a preamble of alternating ones or zeros, or all ones or all zeros. And so we can start with a capture of the dongle and pass this into the XXD utility, which will give us a hex dump of the data. And then we can just grep for stuff that looks like it might be a packet. So we look for repeating ones and zeros, and then we look for the next 4 bytes in the packet, which might be a sync word or header or so forth. And then we just sort by what is commonly found. And then we get this nice byte sequence from the dongle. So we know that this is something transmitted by the dongle. But what we actually care about is what the keyboard is sending. So we do another capture where we record data from the dongle while also typing on the keyboard. And then we can just use sed to get rid of that sequence that we associated with the dongle. We can run this grep command again on the sanitized keyboard data, and we have this new sequence. So we can infer that this is related to packets sent by the keyboard. And so now we can grep for that sequence and what follows, and we find that we have some repeated sequences that are likely going to be the different keys I was typing on the keyboard. And now you can use your normal protocol and packet format reverse engineering tools and skills to figure out what this is. And so it turns out that we have preamble, an address, a sequence number, a frame type, in this case just a keyboard packet. Then we have the actual keystroke identifying the key that was typed, and a CRC. And so the point here is that we've used very, very little radio stuff. We've dragged and dropped 5 or 6 blocks into GNU Radio Companion. We've done some open source intelligence and done some regular binary format analysis, and we've barely touched a radio and have been able to completely reverse engineer the packet format for this wireless device. And to really bring this home, the nice thing about this space is that people much smarter than me have built some great tools that allow you to leverage all of their expertise and treat this as any other software or regular binary reverse engineering problem.
Okay, so to tie it all together, we've proposed this methodology, and we've shown by looking at a series of 3 PHYs that this can be applied to just about every low complexity IoT protocol that's out there. We've also shown that by leveraging open source intelligence, we're able to skip all of the hard parts so that we can get to a point where we can use the skills that we already have to work through these binary formats. So we've shown that all 3 PHYs have some representation of a channel. Modulation is where they deviate the most, but again, we can leverage open source intelligence to make this easier for us. They all have some timing information that has to be recovered. They all contain synchronization features of varying complexity, but things that we can use to start to identify the start of a packet and parse it out. And then finally, once you get to this point, as we've shown, we're just dealing with bits on a disk here. And you can use the skills that you already have as reverse engineers, as software developers, as people who know how computer networks work to figure out what these binary formats mean. So we can repeat this process for any low complexity PHY that we might encounter. So just to wrap up, we've shown that these disparate wireless systems can be rationalized and understood by using process. And we can leverage open source information that's out there to make the really domain-specific and hard, challenging parts of working with radios easy, such that once we demodulate, we're left with bits that we can handle with any tools we please. So one last thought to leave you with, just to inspire you as you go charging out the doors. The IoT is not going to pwn itself. Actually, it already has. It's on you now to develop the radio decoders to start to listen to these devices, find these vulnerabilities, and tell the world. So with that, thank you for your attention. We'll be happy to take any questions with whatever time we have left. I've just been informed we're out of time, so Mark and I will be happy to hang out in the hallway and chat with you guys for as long as you'd like. Thank you.